Hello, this is a review problem session for MCT 2270 Fall 2020 Exam 2. I am, as last time, going to assume that you're able to watch this in HD and the problems behind me are legible. I'm also going to assume that you can follow along with your calculators. I'm not going to show all of my calculations. I'm simply going to show the final formula, and then I've already plugged in the numbers and computed the answers for you. So let's go ahead and get started on these few problems. So problem number 1, a 12,000 kilogram car on a 35-degree slope uniformly accelerates from rest to 60 miles per hour in 15 seconds. What is the average engine power in horsepower? The first note that you're not going to see me do, you'll just get the final answer and know that it's already been done, is that you will want to convert this 60 miles per hour into SI units. Don't forget that step. Okay, the problem is talking about a car on a hill, and this hill is 35 degrees, something like this, and the car is going up the hill. In order to solve this problem, we're going to use conservation of energy, and we're going to need to know the height. Well, if we know the distance that the car travels, using the angle we can find the height. Therefore, my first order of business is going to be to find an equation that gives me the distance. Think back to Tech Physics 1, the kinematic formulas. There are two that we can use here. Now, the distance that we're going to find makes sense to have it be along the slope, like this, all right? So here is what I mean by distance d. It's not completely horizontal, it's the distance the car drives as it's going on that angle, all right? Notice that the car uniformly accelerates, so we can write the acceleration as an average, and we can simply write that as v final, the final velocity, over delta t. Notice that this isn't final minus initial because initial is 0, so I've simply left that off. V final over delta t. The kinematic formulas that we can plug this into to get the distance are as follows. We can have the distance equals v initial t plus 1/2 a average t squared, or we could use v final squared plus v initial squared plus 2 a average times the distance. These are two distinct equations. I hope both come to mind. And I claim that no matter which one of these you rearrange to solve for the distance, both of them give you the same answer. That the distance equals v final times delta t over 2. So either one of those will work. This is a refresher on kinematics. Now that we have the distance, we can then infer that the height that we've gone is simply equal to the distance times the sine of theta. That just comes from trigonometry. You need to think about that a little bit more. Go ahead. All right, so we have an expression now for the height, and we have this in terms of things that we know. Now, we're going to look at energy conservation. What was the change in energy between the bottom of the hill and the top of the hill? So in other words, what was delta E? E final minus E initial. Well, the energy final came from two sources. One is potential energy, or MGH, and the other one is kinetic energy, or 1/2 mv squared. Both of these terms are with this energy final that the car has as it gets to the top of the hill here, at the end of our distance, at the end of 15 seconds. Energy initial is going to be 0, because, I'll say minus, just so you can see where it came from, because there's neither potential energy, if it's sitting at the very bottom of a hill, nor is there kinetic energy because the car started from rest. So the initial energy is simply 0. So this change of energy here, we can write in a different form as the change in energy. I'm just going to go ahead and write it as work, all right? W, because work is the change of energy, all right? So the work is mg, and now for h, I'll plug in our formula from there, which is d sine theta. But notice that if I plug this in for d, I have v final delta t over 2 sine theta. Now you may want to be calculating numbers as you go, and maybe you've already done a side problem, gotten a number, and you can just throw that in here. I'm going to leave this completely symbolic. So this is just simply writing h in terms of all known quantities. So h, v final delta t sine theta all over 2. And then this second term is 1/2 m. And of course this is v final squared, since it's the speed at the very top of the hill. That's our expression for work. And then all we have to do to find the power is write down, let me lift this a little bit. To find the power, we divide all of this by delta t, because power is work over time. So there's going to be a delta t divided through on both terms. mg v final sine theta, all this is multiplied, over 2. Notice that the delta t was in the top, and when I divide by it, it just disappears. And then over here, I have a 1/2, I'll do this over 2 as well actually. We have m v final squared over 2, and here's the delta t. It shows up in that term because there wasn't one already. So here is the formula for solving the answer. And once I've converted my 60 miles per hour, that is v final, into meters per second, which is what I want, I find out that this comes out to about 119,332 watts of power, or in horsepower, like it's asking for, 160 horsepower. All right, second question. Milk weighing 8 newtons is heated on a 1500 watt cooktop that is 40% efficient. How long will it take before the temperature of the milk has increased by 10 degrees Celsius? Use the specific heat of milk of 3,930 joules per kilogram Kelvin. Well, the first thing I noticed is that the mass is not directly given. Instead, the weight is given. This is the only problem on the exam that's like this. But I can simply find the mass by recognizing that since weight is mg, m is weight divided by g. And in this case, when you divide 8 by 9.8, you get a mass of 0.816 kilograms, approximately. So that part is done. We now have the mass of milk that we're dealing with. Well, remember the formula that we use for this. The heat that flows, the energy that flows via heat into the milk equals m times c times delta t, where delta t, this delta t is capital, and this is the change of temperature. So this number will be your 10 degrees Celsius. However, the heat that goes into the milk is not all the heat that comes off the cooktop, because it's only 40% efficient. So this side can be broken out into the heat from the cooktop, or I'll write stove because it's shorter, times the efficiency. Okay? And that's all equal to mc delta t. Now, what I'd like to do is, this is a question about time. So how can I introduce time into this? Well, I notice that I have a power given. And so power and time multiplied make heat in joules. Okay? So remember that this can be written as Q dot stove, or the power from the stove, times the time. Q dot is simply Q over delta T. So to convert Q into Q dot, I multiply by delta T. Still have our efficiency here, and this is MC delta T. An interesting thing to note about this problem is this is a perfect example of why I'm careful with my notation. I have two delta T's in this problem. One is uppercase, meaning a change of temperature, and one is lowercase, meaning a change of time. Okay? The thing that I'm being asked to find is the change of time, so the other two things I'll divide over to get my final expression of delta T equals M times C times the change of temperature divided by the power of the stove, also divided by the efficiency. This efficiency will be a number between 0 and 1, so 40%. That number I'll put in there is 0.4. Okay? So when I plug everything in, using this mass, not using 8 newtons right into there, making sure I convert, put it in, the number that I get out is 53.448 seconds, or on the exam, the answers are given in minutes. So to convert this to minutes, I divide by 60, and I get 0.89 minutes. And I will box the formula as well. Include the whole thing. How's that? Okay? Moving on to the next problem. We have here, water in a river current flows at a velocity of 12 meters per second. Assume the river has a rectangular cross-section with a width of 8 meters and a depth of 3 meters. The current flows over a waterfall, ending in a static pool 40 meters below. How much power could be extracted from the waterfall? Use a density of water of 1,000 kilograms per meter cubed. Okay, before I go ahead and start this, I want to check something. Okay, we're still recording. So what's happening here is that we have a river that's flowing, and I want you to picture this river as being modeled as a rectangle. So what I mean by that is something like this, where this is the flow of the river, and the river basin is rectangular shaped. So as the river flows, there's like a wall of water moving forward. Picture this wall of water moving forward down the river. Now we know that this wall of water, or this slice out of the river, is moving at a velocity of 12 meters per second. And we also know the dimensions of this. We know that its width is 8 meters, and we know that its depth is 3 meters. And again, 12 meters per second tells me that in 1 second, this wall will have moved 12 meters downstream. So if you can picture this, every second we have a volume of water, a chunk of this river that's moving, right? This whole chunk of river is moving every second. So what is that? That's the volume flow. Calculating the volume flow, we have that V dot equals the length times the width times the depth all over time all over 1 second. Okay. And if we multiply these three numbers, we get 12 times 8 times 3 per second, which gives us a flow of 288 meters cubed a second. All right, for the energy, they're asking about how much power could be extracted. So let's think about the power in the top just before it goes over the waterfall, and the power, and then the energy just before it goes over the waterfall, and the energy at the pool in the bottom of the waterfall. Well, before it goes over, it has energy in two forms. It's flowing, so it's got a 1/2 mv squared kinetic energy, and it's also up high, so it's got a potential energy of mgh. At the bottom of the waterfall, it's gone down to 0 height in a pool, so there's no potential, and it's also stopped flowing. We're told that because it's a static pool. So its flow is down to 0 meters per second. It's not moving. So there's no energy at the bottom. Notice that this is a case of the Bernoulli equation, Bernoulli type equation, but we've left out the PV term simply because the pressure at the top and bottom are the same. One's not like pressurized by a piston or a pump or something. It's atmospheric pressure at both the top and the bottom. So that term doesn't have to be here. It's just those two terms that change. So, to find the power, I'll just simply put a dot on everything, meaning per unit time. Now this side of the equation is power. Bring this up here and continue working. And I have an m dot, which I'll pull out of the equation. So E dot equals m dot 1/2 v squared plus gh. The last thing to do is realize that we've got a number for v dot, but we need m dot. And so we simply can convert between a mass and a volume using the density. All right, so m dot is the same as rho times v dot. All right, I'm just simply using the rho as the conversion factor in between. So this is given, that's given, that's given, and that's given. We've got all the numbers that we need. If you plug in all these numbers, we get out an answer for this of 747,000. This is in watts, it's a power. Or if I write it in megawatts, I have 133.75 megawatts. I'll just box up the answer. Okay, for our last question, a 35 psi jet ski pump ejects water at a rate of 392.5 kilograms per second. What is the power of the jet ski in horsepower? Use a density of water of 1,000 kilograms per meter cubed. So the first thing that I'm going to notice to do is do the entire thing in SI units, which means converting this 35 psi. So let me make a note here that 35 psi is roughly equal to 241,317 pascals. So that's taken care of right off the bat, and I won't forget and accidentally plug in 35 where I should be using this number in pascals. All right. Next, I want to set up my equation. I know that I have an energy change between, let me draw a little picture of a pump. In here, there's a water pump and it's being pumped out. It's flowing the whole way, okay? So the flow of water never ends. But what we're going to compare is a little particle of water, a test particle that's inside this pump, and then one that's been ejected. All right? So the energy final let's call this 1 and 2. So the energy difference between E1 minus E2 must be the work, okay? So whatever work is in the system, because work is simply a change of energy, it's the energy difference between the flow at those 2 points. Now, this energy term could have all 3 of these terms. I could have a kinetic term, a potential term, and a pressure term. But in this case, notice the picture. The flow is still going. Beginning and end, it's flowing, same velocity. So I don't have this kinetic term that has velocity in it. It's not changing height, it's completely level. So I don't have this potential term. There's nothing about a change of height. So the only thing I have is this pressure times volume term, okay? That pushing, or that, I forget what I called it. Mechanical pressure, I think is what some people call it, which is like if there's a pump or a piston that somehow changes the pressure at one end of our flow line. Well, that's exactly what this problem is. So this is the time to use this, all right? So this is pressure 1, and then I'll subtract off the energy outside, which is pressure 2 times V. Now I'm not even labeling the V because the volume flow at both points is the same, okay? So my work here is simply pressure 1 minus pressure 2 times the volume. That's work. They ask about power. So all I'm going to do is, like I did with this one, I'll dot the equation. W dot, which means dividing everything by a factor of time. Volume, work dot, which is power, is equal to the pressure difference times the volume dot, or volume flow. Well, we have the mass flow, right? This 392.5 kilograms per second, that equals m dot. So we need to get v dot. Now v dot, we can simply use the density again to convert and recognize that v is m over the density. Okay? So now, this entire expression is in terms of things we know. We know both pressures, we know the mass, and we know the density. What's 1 atmosphere? If it's being ejected out into a pressure of 1 atmosphere on the outside of the pump, well, that's about 101,325 pascals. So the pressure difference is the pressure between these two times the mass flow divided by the density. And numerically, this comes out to be about 54,947 watts is what I believe I have, which is a power of 73.7 horsepower when you convert it. Alrighty? So that's how you do that one. The rest of the exam problems that you may want to have covered are things that we did on Friday. These are just the ones that aren't covered there. So between that and this, we've exhaustively covered all of the mathematical questions that will be on the exam, simply with numbers changed. So good luck, and I'll see you guys later.